Now, there's some basic operations on matrices that are just what you'd expect, and then there's a couple of funky ones, all right? So let's do the basic ones first, and these will be real simple. So it won't surprise you probably that if I have a matrix like this, 2, 4, 5, 9, 6, 2, that I could multiply it by a scalar. So I can say 2a, and if I do that, I'm simply going to get back 4, 8, 10, 18, 12, 4, right? So just like with a vector, if you do scalar multiplication, you end up multiplying the scalar by all of the values, all right? Simple enough. It probably also will not surprise you that if I have a matrix, 2, 3, 9, 7, 4, 2, and if I have another matrix, 1, 0, 1, 2, 4, 5, that I can add these two matrices. And if I add them, I simply add them element by element. 3, 8, 9, 11, 5, 4, right? So element 1, 1 and element 1, 1 get added together to make element 1, 1 of the result. Element 1, 2 and element 1, 2 get added to make element 1, 2, etc. Notice here, and this is not the first time we're going to come across this, or not the last time we're going to come across this, you cannot add two matrices unless they have the same dimensions, okay? So if this is an m by n, and this is an m by n, then you can do the addition. But if this is an m by n, and this is a p by q, where the p does not equal the m, or the q does not equal the n, you simply cannot add them. We're not going to define that operation. So that surprised me at first. I figured if you had a 3 by 2, and you wanted to add it to a 3 by 1, well, you just add this column to both of the columns of the thing, and you'd end up getting it. But not so. Instead, we're going to say that a plus b simply doesn't exist. All right? So that's scalar addition, or scalar multiplication, rather, and matrix addition, very much the same we had with vectors. Now, a new operation here is going to be called the transpose. And this is very simple, but it takes a little bit of doing, so let's make sure we get it. Let's make our A again, and we'll say we've got a 3 by 2. If I say A to the T, that's what it looks like. Now, we don't actually, it's not raising it to a power. This is pronounced transpose. So we call this thing A transpose. A transpose is going to be this. Let's see if you can figure out how I got this. 4, 9, 2, 1, 6, 5. Now, do you see how I got from A to A transpose? Answer is that each of the rows over here became a column over here. So I interchanged the rows and the columns. Which means, of course, that if I have an m by n matrix, then when I transpose it, I'm going to get an n by m matrix, right? In this case, we had a 3 by 2, and then we did the transpose, and we got a 2 by 3. So there will be times when you can't add two matrices together, but if you take the transpose of one of them, maybe you can, right? Because that puts it in the proper dimensions. So those are our three operations. Now, one thing just to talk about this row and column vector business, right? So if I have a row vector here, and again, sometimes it's going to be a row vector, sometimes it's just going to be a vector, and I'll try to be explicit which one I'm treating it as. But right now, let's say we're treating that as a row vector. Then I could say, well, let's take X transpose, and that means what you'd think it would mean. That means turn it into a column vector, right? So the operation of transposing something means simply changing it from a row vector to a column vector, or vice versa, right? If I take the transpose of a column vector, it becomes a row vector, because that is the same thing as simply taking the interchange of the rows and the columns. So when we do that, we're essentially treating the vector as a matrix, right? We're treating it as a 3 by 1 matrix. Take the transpose to get a 1 by 3, or take a 1 by 3, take the transpose to get a 3 by 1. And so that's when we're treating a vector really as a special type of matrix that only has one row or one column.